Good evening. Welcome to Night Science Stories. Tonight we will take a slow walk through the deep time of our planet. Settle in and let your breath find an easy rhythm. I will speak softly as we follow the patient forces that move continents and lift mountains. If you drift into sleep while listening, the story will keep flowing beneath you like a quiet current. Far below our feet, the interior of Earth is not a hollow fire. It is rock that is mostly solid, yet it can flow when time is measured in millions of years. Imagine a landscape made of crystals of olivine and pyroxene, warm and pressurized, moving as if it were very stiff honey. Heat from the core and from the slow decay of natural radioactivity rises upward. Where that heat wells up, the surrounding mantle expands a little, becomes slightly less dense, and begins to rise. Where material cools near the surface, it becomes a little heavier and tends to sink. These motions are faint and grand at the same time. The cycle is convection, and it is the planet's quiet heartbeat. We cannot see this motion directly with our eyes, but we have many ways to listen to it. Earthquakes send waves through the planet, and those waves speed up in cooler, stiffer regions and slow down in warmer, softer ones. By recording thousands of earthquakes, scientists build maps of the deep, as if they were doing a medical scan of a living body. The pictures reveal long tongues that sink toward the core. These are the shadows of old ocean floors that have slid down along great faults at the edges of oceans. They also reveal warm columns that rise from deep below in a few places, feeding volcanic islands that line up like strings of beads. The interior is not still. It is a slow river of stone. Where this motion reaches the surface, the thin shell of Earth cannot stay whole. It breaks into large rafts, the plates of the outer shell, which move because the underlying mantle keeps sliding. The plates carry continents as passengers. They also carry the floors of the oceans. Where plates move away from each other, new ocean floor appears. Where they meet, one can slide beneath the other and sink. The journey is slow. A plate can creep at a speed that you could match with your fingernails. Yet over a few tens of millions of years, those tiny steps add up to journeys that span an ocean. Picture now a long scar that runs down the center of many oceans like a seam on an old leather ball. This is a mid-ocean ridge. Here, hot mantle material rises and partially melts as pressure eases. The melt gathers in small chambers and feeds cracks at the surface. Basaltic lava flows out, often underwater, and as it meets the cold sea, it forms smooth, rounded shapes that look like stacks of pillows. A new strip of oceanic crust is born. The ridge itself is not a single peak but a ragged chain of mountains that stretches around the world, a wound that is always healing and always opening. The space above these ridges is a world of chemistry and life. Seawater percolates down through cracks until it meets hot rock. It heats, reacts, and rushes back out at vents as a dark, mineral-rich fluid. The fluid looks like smoke, but is water-loaded with fine particles of metal sulfides that form as the hot liquid meets cold seawater. Around these vents are communities of creatures that do not rely on sunlight. Bacteria use chemical energy from the vents to build sugars, and larger organisms, including tube worms and clams, host these bacteria in their tissues. In the darkness, a food web thrives powered by reactions that begin in rock and water. When we watch the vents, we are seeing a conversation between mantle heat, seawater, and life. If we could glide over the ocean floor from a ridge toward a distant continent, we would cross a pattern that looks like a barcode. Long stripes of rock on one side of the ridge mirror similar stripes on the other side. The stripes are made not by color but by tiny magnets inside the basalt. When lava cools, crystals of magnetite lock in a record of the direction of Earth's magnetic field at that moment. The magnetic field is not fixed forever. From time to time it flips so that a compass that once pointed north would point south. These flips do not follow a simple schedule, but when they happen, new lava cools with the reversed direction. As the seafloor spreads away from the ridge, it carries the magnetic memory with it. The ridge writes a symmetric diary of Earth's field into the ocean floor. When this diary was first read, it gave the world simple proof that the surface of the planet moves outward from ridges. The stripes are the patient handwriting of the sea. There is another quiet measurement that makes this motion feel real and immediate. Many places around the world carry small radio receivers that listen to signals from satellites. These receivers measure their positions with astonishing precision. When we compare positions month after month and year after year, we see cities move by a few millimeters, sometimes a few centimeters. The Pacific Northwest inches toward Alaska. Parts of Australia slide north. The Atlantic grows a little wider as North America and Europe drift apart. The numbers are small but unsleeping. In one human lifetime, a plate can travel a distance that a person could walk in an afternoon, and in that time, mountains rise a little and fault lines breathe. Where plates meet, the encounter can take several forms. In many places where the ocean floor meets another plate, the denser oceanic crust and its upper mantle begin to slide downward into the mantle beneath. This is subduction. The place where the descent begins is marked at the surface by a deep trench in the ocean. The angle of the sliding slab varies with place and time. Water goes down with the sinking crust, locked in minerals that formed on the sea floor. As the slab plunges to greater pressure and temperature, those hydrated minerals break down and release water into the overlying hot mantle. The water makes that mantle melt more easily. The melt rises to feed volcanoes that line up in an arc above the sliding slab. Farther landward, the crust is bowed down by the pull of the slab and by the weight of sediments and volcanic rocks. Outboard, near the trench, sediment scraped from the sinking plate jumbles into a wedge that grows by accretion. The whole system operates as a giant slow conveyor that recycles ocean crust into the interior and builds new crust at volcanoes near the surface. These volcanic chains form graceful arcs because they trace the contour above the sinking slab at a fairly constant distance from the trench. The chemistry of their rocks often shows a signature of water-rich melts. Andesite and dacite are common, richer in silica than the basalts of the ocean floor. The landscape wears cones and calderas, snow and ice on the higher peaks, forests on the lower flanks. The air around these ranges is full of tiny crystals of volcanic glass when eruptions occur, but most days it is quiet, with thin steam rising from vents and warm springs curing the chill of mountain valleys. The word arc is not only a shape, it is a rhythm. These volcanoes are young and watchful. They grow grain by grain over thousands of years, and from time to time they reset their profiles with an eruption, then return to the slow business of building. There is another kind of mountain that rises when two continents meet, Neither continent is dense enough to sink easily. When they collide, they crumple and thicken. The crust piles up, and the deep roots of the mountain thicken as well. Imagine the meeting of India and Eurasia. Between them once lay an ocean floor that was consumed by subduction. As the gap closed, fragments of that old ocean floor were sometimes thrust up and welded onto the edge of the continent. These fragments are called ophiolites. They are souvenirs of a vanished ocean preserved on land. When the last piece of oceanic crust vanished, the continents pressed together and a broad plateau began to rise. Rocks that once lay many kilometers down became exposed at the surface. Fossils that formed in shallow, warm seas now rest near the feet of glaciated summits. The mountains speak of travel long completed. Even mountains that pierce the sky are not free to grow without limit. The crust floats on the softer mantle below it, much like an iceberg floats in water. This state of balance is called isostasy. If the crust becomes thicker in one area, it sinks a little deeper until the buoyant forces match the weight. If material is removed from the top by erosion, the root rises a little. The balance is dynamic. Picture a wooden raft loaded with stones. As you remove stones from the top, the raft rides higher. In the crust, the timing is measured in thousands to millions of years, but the principle is as simple as a child's hand in a lake. The roots of great mountain ranges reach far below what we can see. In some ranges, the crust can be twice as thick as average continental crust. The thickening creates a root that swims in the warmer mantle like the lower block of an iceberg. We can sense these roots through seismic waves that travel more slowly through thick, warm crust than through thin, cooler crust. Gravity measurements also reveal their presence. Over time, the roots themselves can change. Parts may become dense due to changes in their minerals at depth. Those dense parts can detach and sink, like a stone breaking free from a raft, allowing the overlying mountains to rise or the surface to relax. The mountain we see is only part of a deeper structure that finds its equilibrium again and again. While these balances play out, the surface of a mountain range is being carved. Erosion is the patient sculptor. It uses sunlight, water, ice, wind, and even life to move grains of rock from high places to low. Chemical reactions loosen minerals and turn some rocks into clays and iron-rich soils. Frost wedges rocks apart when water seeps into cracks and freezes. Glaciers grind and polish valleys and carry fine flour of rock many kilometers. Rivers cut channels and wander, lifting stones in floods and laying them down as bars when the energy wanes. Plants and microbes pry apart grains with roots and acids, then hold the soil as it moves. None of this is hurried. A cliff that feels solid under your hand today is a story in progress, written line by rain and thaw and the growth of a lichen. As erosion removes mass from a range, isostasy responds. The crust that was pressed down by the weight of tall peaks begins to rise a little. This rebound can keep the highest parts of a range near the sky even as their rocks are removed and carried away. In some places, the rebound after the melting of a great ice sheet is still lifting the land today. Quietly, some northern shorelines are rising by the thickness of a finger each year. Old ports are now stranded above the tide. Lakes tilt slightly and their waters find new paths. The ground remembers the weight of ice and the relief of its departure. Every grain that leaves a mountain must go somewhere, Rivers are the movers. They carry sand, silt, and clay, as well as dissolved minerals, toward basins that lie at lower elevation. When the river slows, it drops part of its load. On the plains, it spreads out in wide sheets during floods and leaves new soil that makes fields fertile. At the foot of slopes, it may pour out of a canyon and spread into a fan. Where a river meets the sea, it builds a delta that crawls outward over centuries like a many-fingered hand. For a time, the weight of this new pile of sediment bends the crust downward like a wooden board sagging under a bag of grain. The bend makes more room for sediment. Layer builds on layer, each telling a story of a season or a storm, a sand drought or a muddy flood. In time, some of these layers may be carried back toward the place where mountains grow at subduction zones. There, the sediments can be compressed, heated, and lifted, and the cycle runs again. This exchange between high and low is a quiet partnership rather than a battle. Mountains rise because the crust is thickened by the meeting of plates and by the flow of the mantle below. Mountains also rise in response to the removal of mass from their shoulders. Plains grow because rivers feed them with the gifts of distant heights. Plains, in turn, load the edges of continents with sediments that become the raw material of future rock. In this way, the planet writes a long poem where the themes return with variations. Ocean becomes mountain, mountain becomes plain, plain becomes a future mountain as plates carry the story into another age. If you listen closely, there are small and rare facts tucked inside these grand motions. Basalt made at mid-ocean ridges often carries a trace of helium that is older than the continents, a whisper from the young Earth that escaped into the bubbles of lava. Sand found in a desert dune can contain grains of zircon that formed before any animals walked on land. Grains that have survived many cycles of erosion and burial and uplift. A limestone taken from a high plateau may hold the shells of tiny sea creatures that settled in warm, shallow water millions of years before their home was raised toward the sky. These details are like notes in a lullaby. They do not surprise the song. They give it texture. You can feel the patience of these processes even in an ordinary landscape. Stand on a low hill and watch a river bend. The outer bank erodes, the inner bank receives. Grass clings to the top of the outer bank until undercutting takes it down in a quiet slump. A tree near the bend leans a little more each year and then lies in the water where fish hide in its branches. Far away, a ridge casts a blue edge against the afternoon. The air carries the scent of soil after a last shower. Nothing is still, and nothing is in a hurry. Imagine now following one grain of quartz. It rests in a hard vein inside granite, deep below an ancient range. Uplift brings it nearer the surface, and frost one winter loosens the rock and frees the grain. A stream picks it up and rolls it down a slope where it settles for a season behind a log, then moves again in a spring flood. The grain travels by many short steps toward a plain. It becomes part of a sandbar, then part of a dune, then part of a delta. It is buried and slowly pressed. After many lifetimes, it turns to sandstone. The plate under the sandstone moves, and part of the rock is carried down in a subduction zone. Some of its material melts and rises into a new chain of volcanoes. In time, that chain is uplifted into mountains. One day, a block of the new rock reaches the surface and breaks, and our grain is freed once more. The planet has a patience that is kind. The drifting of continents is often told with maps that show shapes sliding around like pieces on a calm sea. The reality includes memory and feedback. As a continent moves, it changes wind and rain patterns that sweep across it. If a plateau rises, it can cast a rain shadow that turns a region downwind into steppe and desert. If a mountain belt lowers, a coast can become greener. In the tropics, the growth of great ranges can even strengthen the cycle of monsoon winds that bring seasonal rains from the ocean. The landscape and the air are partners. What rises on the ground can alter what falls from the sky. These changes are never a single cause with a single effect. They are woven effects that slowly reshape a planet that remains familiar. Rivers still cut meanders. Grass still bends under wind. The ocean still brings smell and salt to the shore. The slow movements beneath the crust simply tilt the stage on which these daily actors perform. A ridge tens of kilometers below a mountain valley can cause a spring to emerge where someone will one day drink and rest. A fault that slips a few millimeters each year can create a gentle scarp that forces a small stream to braid and wander. A trench thousands of kilometers long can be the reason an arc of islands has rich soil for forests and farms. The deep and the near are connected. If you are still awake, picture the world map as a living thing. The Atlantic is widening a little each year, not enough to notice from a boat, yet enough to matter in 1,000,000 years. The Pacific is closing. Somewhere on the floor of that ocean basalt that cooled last night has already begun its journey toward a trench. Somewhere at the edge of a continent, a few grains of sand joined a growing delta. Somewhere in a mountain, a tiny crystal of garnet grew inside a rock that is slowly traveling upward. The planet that carries us is not racing. It is drifting with confidence. We have walked together from the soft motion of the mantle to the place where oceans are born, down the barcode of the magnetic sea floor, across the measuring lines of satellites, into the shadows of trenches and the glow of arcs, up the sutures of colliding continents, into the floating roots of ranges, through the art of erosion, and out onto the plains where rivers deliver gifts. The lesson is one of comfort. Change can be gentle and sure. A restless mind can borrow that pace and let go. Far to the north and far to the south, a quiet weight presses on the crust. It is the weight of ice laid down by many winters. When ice collects into a sheet that is kilometers thick, it bows the crust down. Rock flows very slowly beneath it, making a basin where the ice sits. Around the edge, a raised rim forms where pushed rock has gathered. When a warm time arrives and the ice melts away, the weight is removed and the crust begins to rise. It does not spring back in a single season. It rises like a slow breath taken by stone. Shorelines tilt, rivers find new paths, ancient harbors are left high above the tide. People still walk across beaches in parts of the north where waves once washed, and they stand among old anchors that now lie in grass. The land is returning to balance, and that balance is called isostatic rebound. The memory of ice reaches even into gravity. When satellites map the strength of gravity over the planet, they find a gentle low in the region of a great inland sea. The crust there is still rising and the mass of rock is still rearranging itself after ice departed thousands of years ago. Some lakes nearby have shorelines that look like the lines on a bathtub. each one a record of a time when the water found a different level because the land was lifted unevenly. In one region, stones that were once on the sea floor are now stranded far above the waves, carried there on plates of ice that melted and left them like messages on a hill. All of these scenes whisper the same idea. Ice has weight, rock flows, the crust breathes in response. Rebound is not the only change that ice brings. As the weight lifts and the crust rises, faults wake and adjust by small amounts. Earthquakes occur in places that are usually quiet. The heart of a continent feels a series of slow aches that release long-stored strain. In coastal places, rebound can lift land faster than the sea rises, and new birch and spruce colonize marshes that were recently under salt water. The opposite can happen near the outer rim that was once raised by the ice. That rim may sink a little as the center rebounds, and marshes there may flood. In these gentle shifts, we see how water in its many forms shapes the skin of the planet. From ice and isostasy, let us drift to a different source of motion. In a few places, hot columns of mantle rise from deep levels and feed long-lived centers of volcanism. These upwellings are called plumes by many geologists, and the places where they pierce the surface are called hotspots. Picture a belt of oceanic crust moving slowly over a fixed source of heat. Where the belt passes above the source, volcanoes grow from the sea floor and sometimes break the surface to form islands. As the plate continues to move, the volcano that once had a steady supply of melt is carried away and it goes quiet. A new volcano forms nearer to the source and takes its place. Over millions of years, this process makes a chain of islands and seamounts that trace the path of the plate across the deep engine below. One notable chain bears a graceful elbow. The older underwater peaks point in one direction and the younger islands point in another. The bend marks a change in the direction of plate motion that happened long ago. The islands themselves share families of lavas that reveal the chemistry of the source and the degree of melting that fed each stage of growth. Some of the rocks are full of gas bubbles that later filled with crystals of green olivine and pale zeolite. Some hold rare fragments of deep mantle lifted to the surface as if carried in a glass elevator. The islands also tell the story of erosion and subsidence. As a volcano ages and is carried into cooler water, the crust beneath it cools and sinks. Waves and weather plane the summit down so that a once bold island becomes a low coral ring after the summit slips below the waves. The ocean holds many such rings, silent blue circles that mark the former heights. Hotspots can occur under continents as well. In some lands, odd clusters of small volcanoes rise across broad plains. They erupt unusual magmas that move quickly through the crust and occasionally carry diamonds from deep sources. The diamonds arrive embedded in pipes of dark rock that solidified from very fast-moving melts. Miners find these pipes by careful mapping of subtle clues at the surface, and each pipe is a diary of a rapid journey from high-pressure realms to a quiet field. In other regions, huge outpourings of lava occurred in ancient times, covering areas the size of countries in stacked sheets. These events were rare and dramatic compared with the steady breathing of normal ridges and arcs. They changed air and climate and left behind plateaus of basalt with step-like cliffs that shine in evening light. The patient motion of plates sets a rhythm. Hotspots and mantle floods add rare symbols to the score. The stage on which all this occurs changes through a long cycle that joins oceans and continents in a repeating pattern. It begins with a rift that opens in a continent. The crust thins and the land splits along a line of faults. Volcanic activity accompanies the stretching as mantle melt rises along the cracks. Gradually, a narrow sea forms, and then an ocean with a newborn ridge at its center. For many tens of millions of years, the ocean widens, and its floor grows outward from the ridge. But plates are never content to move in only one pattern. At some point, new zones of subduction form along the edges, and the ocean begins to be consumed. Island arcs grow. Continents move closer. In the end, two continents may meet and stitch together. Mountains rise along the seam. The joined mass rests for a time as a supercontinent. Heat builds under its broad blanket, and eventually new rifts crack it apart, and the cycle begins again. This long story is called the Wilson cycle. Evidence for this cycle is written in belts of metamorphic rock that mark ancient sutures where continents joined. It is written in fossil patterns that show creatures wandering across lands that were once neighbors but are now far apart. It is written in the ages of ocean floor rocks, which are all younger than 250 million years, while continental crust holds terrains billions of years old. Oceans are temporary theatres. Continents are long-lived actors who change costumes again and again. Supercontinents have gathered and parted several times. The most recent grand assembly is the one often shown on classroom maps when the land was gathered into a single mass that we call Pangaea. Before that time, there were older unions with different shapes and names. One of them gathered most of the continents around the equator and has the lyrical name Rodinia. The pieces of that one later drifted apart and recombined in new arrangements long before the first trees appeared on land. We hold fragments of these stories in the paleomagnetic directions recorded in old rocks. When a rock cooled, it kept a memory of which way north lay at that time. By measuring many such memories, geologists can turn the pieces like tiles until the directions match. The shapes of matching coastlines and the positions of ancient mountain belts confirm the fit. In the basement of some continents, you can stand on rocks that were once neighbors to stones now a world away. The planet remembers its families even after they scatter. There are lesser-known souvenirs that attach our thoughts to deep time. A small crystal of zircon found in a sandstone from a dry region has been dated to nearly the dawn of the planet's history. It survived cycles of weathering and burial and metamorphism, and still carries within it a clear signal of age and even a hint of the water-rich conditions under which it first grew. A pebble polished by waves on a beach in a landlocked desert shows that a shallow sea lapped there for a time when continents were joined in a way no human saw. Under the high grasses of a plain, a belt of dark rock marks the trace of an ancient rift where a supercontinent began to part. These are quiet footnotes in the Book of Supercontinents, enough to carry a mind into the long evening while the body settles into rest. To watch motion today, we do not have to guess. We can measure directly. Small receivers on bedrock and on buildings listen to signals from satellites that circle the planet. The stations are tied into a stable frame based on distant quasars that sit far beyond our galaxy. Using this steady background, the stations can report their position to the thickness of a coin. After months and years of quiet recording, the results show movement that is both small and relentless. A town in the south of a large continent glides north by a few centimeters each year. Islands in an arc draw closer together. Points on either side of a fault creep past one another with steady grace, saving a little motion for the day when strain will be released by an earthquake. On the far side of the ocean, another chain of measurements shows drift in a different direction. The map becomes a slow movie. People like to say that continents wander. With these instruments, we see that they do so with the patience of stone. Satellites also measure how the surface rises and falls when a big fault slips or when a volcano swells with magma. They send radar that bounces from the ground and returns with tiny changes in distance. By comparing images taken on different days, scientists can map a bulge on the flank of a volcano that is smaller than your height. They can also watch the ground around a city and see where it sinks or lifts due to water use or the rebound of old ice. In these images, the planet looks like a sleeping chest that rises and falls almost imperceptibly with the quiet breath of stress and release. Even without an eruption or an earthquake, the daily background shows slow changes that speak of mantle flow and of crust that bends under loads and recovers when the load changes. Not all pieces of continents travel as single blocks. Along many edges, small bits arrive as passengers and are welded to the margin. These fragments are called terrains. Some are the cores of islands that lived alone for a long time. Some are slivers of ocean floor that were scraped off and piled onto the continent when a plate slid beneath it. Some are microcontinents that rifted away from a larger mass, floated for a while, and then found a new home on the side of a different land. In some mountain belts, you can walk along a valley and cross from rock types that formed near the equator to rocks that formed near the pole, each one carrying fossils that speak of a very different climate. The only way this makes sense is to picture these fragments traveling long distances before joining the range. Terrains can bring mineral riches. They can also bring their own peculiar structures, so that a traveler crosses many crustal worlds in a single day's walk. The pattern resembles a quilt with patches from many wardrobes sewn together into a cloak that keeps the continent warm. At the scale of human life, the edges of continents often look quiet. At the scale of deep time, they are busy docks where ships of stone unload their cargo. While mountains and terrains capture the eye, there is another form of slow change that acts on the interior of continents. It is not the result of collision. It is a broad lift or gentle subsidence of large regions that do not break or fold. The word used for this is epirogeny. The causes can include flexure under the load of sediments, thermal changes in the lithosphere, or the push and pull of currents in the mantle that flow on scales of many hundreds of kilometers. If warm material rises beneath a region, it can lift a plain by a few hundred meters over millions of years. If cool, dense material gathers beneath, the land can sink and a wide, shallow sea can return. Ancient shorelines mark such visitors in the rock record. Dinosaurs once walked on beaches that are now thousands of kilometers from the nearest tide because the interior of the continent rose after those seas drained away. Modern instruments hint at these gentle movements. Rivers that once flowed across featureless plains now show a steady increase in relief along their courses. Waterfalls retreat upstream in landscapes that are slowly lifting. Some lakes tilt so quietly that only a long line of old piers shows the change. This dynamic topography, driven by flow in the deep mantle, writes its story with a very light hand. Under the right evening light, you might see it in the way a horizon line sits ever so slightly higher than an old surveyor's mark. Across oceans, another kind of boundary moves differently. Two plates can slide past one another rather than collide or spread. The boundary between them is a transform fault. Motion along these faults takes place in small steps over long time. Pieces of crust that were once neighbors can be separated by hundreds of kilometers while remaining aligned. In the deep sea, transform faults offset segments of mid-ocean ridges and create valleys with ridges on either side. A long continent's transforms can make long linear valleys and ranges that run beside them. People living near such a fault can feel sudden releases of the stored motion as earthquakes when a locked patch finally yields. But even when no quake occurs, the plates continue their patient glide, and the landscape records it with streams that change course and rocks that ride past each other with matching layers now separated. The quiet part of transform motion is not only the slow creep, it is the way landscapes adapt. A river that met the sea at a certain point can be shifted along the fault over time so that it finds a new outlet. A ridge that crossed the fault is broken and displaced so that its halves no longer line up. Geologists trace these offsets like detectives following clues across scrub and grass. Some of the most famous offsets show rocks of the same age and type, sitting on opposite sides of a valley separated by the work of centuries and millennia of slip. The evidence sits in sun and rain with no sign of hurry. Beneath all of these motions is the rock cycle, a quiet circle of change that turns igneous rock into sediment, sediment into metamorphic rock, and all of them back again. When a rock is buried and heated, its minerals begin to rearrange. At first, they may become slightly larger and more orderly. Then new minerals may grow that are stable at higher pressure and temperature. In some metamorphic rocks, minerals grow into long, thin crystals that align under pressure and give the rock a sheen that catches the light. Garnet can appear as small red crystals in a shimmering matrix, each crystal a tiny clock that records the conditions of its growth. Fluids move through these rocks and carry elements that can form new veins when conditions change. The result is a deep art of chemistry and texture. Under yet greater heat, rocks may begin to melt. The melt rises and cools to form granite deep underground. If uplift removes the cover, that granite appears at the surface as rounded domes or as cliffs that glow warm at sunset. At the same time, other rocks are exposed to wind and water, fall to grains, and are carried away to basins where they become layers of sand and mud. These layers may later be folded and pushed into a mountain belt, where heat and pressure transform them again. Some cycles close quickly in geologic terms. Others take so long that continents change partners while the story unfolds. Through it all, a single grain of mineral may see many worlds within the same planet. At this quiet hour, it is natural to wonder what comes next for mountains and oceans. If the long rhythm of the Wilson cycle continues, the present map is a moment within an ongoing dance. In the far future, a new ocean may open within a continent where rifting begins today. A different ocean may be closing under a belt of island arcs that will one day be part of a mountain chain on a large landmass. The wash of shores along one coast will look out on a smaller sea bounded by rising ranges. Another coast will feel the long swell of a growing ocean and see new basalt being born along a ridge far away. Some scientists explore scenarios where the present continents gather again. They draw maps with a single landmass straddling old poles or hugging the equator. The details differ, but the theme remains that continents are travelers who sometimes camp together for a long season before parting. In those maps, new deserts appear where winds are blocked by high plateaus, and new forests appear where warm currents and mountain shadows invite rain. Rivers redraw themselves across the new heights and drop their load into seas that never existed before. Creatures adapt. The sky writes new routes for storms. The planet remains itself. What will happen to a particular mountain range can be told in hints. If a range sits above a thriving subduction zone, it will likely continue to rise as long as ocean floor feeds the melting mantle below. If a range was born from a collision of continents, it will grow for a while, then settle into a long age of erosion and isostatic adjustment. The highest peaks will soften, the streams will carve deeper. In a distant age, the old suture may be an unassuming valley where a traveller walks among fossils that formed when the sea returned for a time. Nothing in this is rushed. A valley that looks new to us could be millions of years old. A ridge that looks eternal is a page that will turn. Even the deep structure changes. A thick mountain root may become denser and drop away in a drape-like fall called delamination. When that happens, the buoyant crust above can rise a little and the surface may lift in a broad swell. Later, the area may settle as the lower crust cools. Over very long spans, the mantle flows in patterns that lift some regions and lower others for reasons that have nothing to do with local faults or folds. Where warm material rises, plains can become high plateaus with rivers that have more energy to cut. Where cool material sinks, a shallow sea can flood a land and leave chalk and limestone to mark its visit. Tonight we have followed a slow procession. Ice sheets press and let go, and the crust sighs with relief. Plumes rise and leave trails of islands that bend with time. Oceans open and close and stitch continents into grand quilts, then cut the stitches and begin anew. Memory lives in tiny crystals that predate forests and in magnetic stripes that run for thousands of kilometers under green water. Receivers on quiet hills watch the planet move by the breadth of a fingernail each year. Small fragments arrive at continental docks to be sewn into ranges. Planes lift and sink under forces that come from far below. Plates slide past with the patience of old friends who do not hurry. Rocks change clothes in heat and pressure and become something new. The map of tomorrow grows from these actions without noise. If you are still awake, imagine the globe slowly turning in space. Night slips over one ocean while day brightens another. Under the thin crust, the mantle continues its slow dance. A new strip of basalt cools along a ridge. A set of light earthquakes marks the place where a plate dives under another. A glacier carves a small berg into a cold sea. A river picks up a grain of sand and carries it one bend closer to a distant delta. Somewhere a mountain lifts by a fraction of a millimeter because a thick root warmed and expanded. Somewhere else a plain settles by the same small amount as the mantle breathed outward. No trumpet announces these changes. They collect into futures. Rest now inside that patience. The planet will keep its slow schedule while you sleep. In the morning, the world outside your window will seem exactly the same, yet the continents will have moved by a small kindness of distance. Mountains will have gained or lost the thickness of a hair. The deep will have traded a little heat with the shallow. Everything will still be here. Everything will be on its way. Along some continents, the edge of the land meets the ocean with a sense of ease. These are passive margins. They are not ruled by the loud meetings of plates, but by slow cooling and steady sinking. Long ago, these shores began as rifts that opened and filled with a new ocean. As the young oceanic crust drifted away and cooled, it became denser and heavier, and the edge of the continent gently subsided beside it. With that gradual lowering came wide shelves and smooth slopes, places where rivers could deliver their loads. Sand and mud spread outward in sheets and tongues, stacked by storms, tides, and currents into a quiet archive that thickens through millions of years. If you could walk on the sea floor along one of these shelves, you would see ridges made by waves that passed seasons ago, and furrows carved by storms that came once in a decade. You might cross the head of a submarine canyon that begins near the shelf edge. During rare floods, dense flows race down these canyons, carrying sand from a river mouth into the deeper sea. The flows settle into layers on the slope and beyond, making beds that start with coarse grains and grade into fine ones. Each bed a memory of a single event. Farther out lies a vast rise built of many such beds, a gentle ramp at the foot of the continent. Here and there warm shallow banks grow reefs or carbonate plains, where tiny creatures assemble chalk and limestone from dissolved shells. Barrier islands migrate slowly, marshes thicken like quilts, and the shoreline inches forward or back as rivers and waves negotiate a truce. It is a coast that moves in the language of patience. To understand how such peaceful edges begin, turn inland to places where continents are stretching. The crust pulls apart, and as it thins, it breaks along normal faults. Long blocks drop down to form grabens, and the blocks that remain high become horsts. In these sunken valleys, lakes gather. They can be narrow and deep and very old, with quiet waters that layer fine sediment year after year in delicate couplets. Dark volcanic dikes slice upward to feed small lava flows. The mantle below rises a little to fill the space left by thinning, and the warm rock reduces in pressure enough to melt. The melts find fractures and take them as paths to the surface. The pattern of faults sometimes organizes into a three-armed junction, like a Y laid on its side. Two arms can win the contest and open into a young ocean, while the third arm stalls and becomes a valley that points like a fossil arrow. As the rift matures, the land splits to let in seawater, and a narrow sea appears. Margins that were once active with faults become quiet as the new ocean settles into its life. The story of a calm shoreline is therefore the echo of an old fracture, healed and breathing slowly. Beyond volcanic arcs that guard the edges of many oceans, another kind of basin can form. When an oceanic plate sinks into the mantle, the slab can roll back towards the sea. As it does, the area behind the volcanic arc can stretch. That stretching opens a back arc basin. In the floor of such a basin, seafloor spreading can occur on a small scale. There are ridges and vents, much like those in the great mid-ocean belts, but here they sit behind a line of volcanoes that are fed by water released from the sinking slab. The crust in back arc regions is often thin. The basins can be temporary seas whose outlines shift as the subducting slab changes angle and speed. The chemistry of rocks in these basins tells of mixed influences. Some lavas resemble mid-ocean basalt, others carry the flavor of arc magmas that rose nearby. Hydrothermal vents here also host life that thrives on chemical energy. The vents can enrich the sea floor with unique mineral deposits that grow in black chimneys where hot water meets cold ocean. The geography of the basin is restless in a slow way. Spreading may start and stop. Faults rise and die. Islands appear, link, and divide again. It is a world that records both tension and compression, an inland echo of the greater meeting of plates at the trench. Return now to the very front of that meeting. At the trench where an ocean plate descends, soft sediment on the sea floor is not always pulled down smoothly. Much of it is scraped off and piled into a wedge that leans landward. This wedge is an accretionary prism. It grows by small additions, layer after layer, as mud and sand are thrust upward along gently dipping faults. Inside the prism, slices of old sea floor and slumped sediment are folded and pressed together. Fluids freed from the sinking crust rise through the wedge. They reduce friction and help the layers glide. Now and then the fluids reach the surface at cold seeps where communities of clams and tube worms gather to harvest chemical energy from methane that leaks from the sediment. Mud volcanoes build gentle cones where slurry oozes and dries, then oozes again. An accretionary prism looks chaotic from the outside, but there is an order in its growth. Each new slice pushes the older ones upward and landward. The wedge finds an angle that lets it barely resist sliding, and then keeps that angle as it grows. It is like a pile of damp sand at the foot of a board. Add a little more and part of the pile slips, keeping the slope nearly the same. The prism records earthquakes too. Some faults inside it creep slowly, others lock and then slip in a sudden shiver. The wedge rises grain by grain over the ages, a slow construction project at the edge of the world. On the other side of a rising mountain belt, the weight of rock bends the crust downward to make a long basin that hugs the range. This is a foreland basin, a place where rivers carry the gifts of the mountains and lay them down in thick packages. Coarse fans of gravel spill from canyon mouths and grade into broad plains of sand and silt. Farther out, lakes and shallow seas come and go as the basin deepens or fills. The load of new sediment makes the crust sag a little more, which invites more sediment. The basin migrates as the wedge of mountains grows and shifts. In the rock record, the result can be a grand alternation. First, deep water muds and sand, rich in marine fossils, lay down while the basin was deep and quiet. Then, as the mountains delivered more and more material, the basin shallowed and was filled by river plains and deltas. The sequence is a story of burden and response. These basins preserve the blush of a mountain in youth. Pebbles show which valleys were active. Sand grains record the kinds of rocks being eroded. Paleosols mark pauses when the landscape breathed and plants covered a floodplain. Coal seams tell of swamps that were drowned and buried. When we read this book of layers, we see the mountain not just as a peak but as a source, a fountain in stone whose waters are sands and clays that flow outward and settle in patience. Not all subduction dips steeply. In some settings, the sinking plate glides beneath the continent at a shallow angle for a long distance before it finally sinks deeper. This is flat slab subduction. The shallow geometry increases the contact between the plates and transfers compression far inland. Volcanism that would normally mark a neat arc can be muted or shifted far from the trench. The surface response can include broad uplifts and the rise of ranges in places that might otherwise have remained quiet. Rivers that crossed a plain may now meet low ridges set athwart their path. The entire region takes on the air of gentle pressure applied by an unseen hand. Flat slabs may carry topographic features of the ocean floor with them. If a buoyant plateau or a chain of seamounts approaches the trench, it can resist sinking and help hold the slab flat for a time. Where such features pass under the continent, they can crumple the crust above and change fluid pathways. After the buoyant feature passes, the slab can steepen again, and the volcanic arc may reawaken in a new position. The silence and speech of volcanoes in these settings are part of a careful dialogue between geometry, density, and water. Sometimes the subducting plate tears. A spreading ridge can also run into the trench and be pulled under, leaving behind a gap in the sinking slab. This creates a window. Through such a window, warm mantle can flow upward into places that were once shaded by the cold slab. The change in heat and flow can spark unusual volcanism on the overriding plate. Rocks erupted above a slab window can look different from typical arc lavas. They can include magmas, more like those at mid-ocean ridges, mixed with melts of continental crust. Heat flow at the surface may rise. Springs may change their chemistry. In some regions, the track of a subducted ridge is marked by a band of volcanic centers that do not fit the usual arc pattern. Their position and age march along in step with the imagined path of the window. Geologists trace these hidden architectural changes with many clues. Seismic waves show where the slab is present and where it fades. The age of volcanic rocks traces the migration of heat sources. Gravity and magnetics reveal buried ridges and plateaus that once rode the plate into darkness. It is a reminder that the surface is a calm room built on a shifting framework. A missing wall in that framework lets a different breeze move through. Mountains do more than tower. They change the air and the long, slow cycle of carbon. Fresh rock lifted to the sky is exposed to rainwater and to the weak acids made by carbon dioxide dissolved in that water and by the breath of soils. Silicate minerals react and yield ions that rivers carry to the sea. There, the ions help build shells and skeletons of marine organisms. When those shells settle and become limestone or other carbonate rock, a tiny portion of carbon is removed from the air and tucked into stone. Over millions of years, this process acts like a thermostat. When climates warm and rain falls more, weathering can speed up and draw carbon down. When climates cool and weathering slows, Volcanoes that continue to bring carbon from the interior can slowly rebuild the supply in the air. The details depend on rock type, temperature, vegetation, and the way mountains channel clouds. Basalt weathers more quickly than granite. Steep slopes deliver fragments faster to rivers. Glaciers grind rock into flour that reacts quickly with water in faraway plains and coastal seas. Plant roots and microbes release organic acids that help break minerals apart and carry the products into streams. In some mountain lands with heavy monsoon rains, rivers deliver huge loads of dissolved material each season. The effect is not a switch that flips year to year. It is a balance that plays out over spans that hold many ice ages and many summers. Mountains rise and invite reactions. The air replies in a soft voice, and after a long conversation, the planet finds another comfort level. Some of the most remarkable conversations between water and rock happen deep below, where ocean crust and mantle rocks meet seawater along faults and fractures. In these places, cold water percolates down and meets warm ultramafic rock, rich in olivine and pyroxene. The water reacts and becomes part of new minerals. The rock changes into serpentine, a flaky green mineral that is slippery and lower in density. Magnetite can form as iron is rearranged. The reactions release hydrogen and small organic molecules. These gases feed microbes that live in the dark, creating tiny ecosystems powered by chemistry alone. Serpentinization changes the strength of the oceanic plate. It makes some layers softer and easier to deform. It can lubricate faults and contribute to slow slip events and tremor at the base of subduction zones. In some lands where slabs were once thrust up onto the continent, slices of old seafloor and mantle rest in mountains as ophiolites. Streams that run from these rocks can carry the signature of serpentinization. In carefully designed experiments, crushed ultramafic rock reacts with water to trap carbon as solid carbonates. Nature does this too, slowly, in veins that crisscross the rocks with white ribbons. The process suggests a patient path by which part of the carbon we release might someday be tucked back into Earth, not as gas, but as solid stone. There are rocks that tell of journeys to depths not usually imagined for continental crust. In some mountain belts, metamorphic rocks contain minerals that can only form at pressures corresponding to very great depths. Coesite is a dense form of quartz that forms when pressure is high. Tiny diamonds appear in some rocks that were once part of the crust that rode down on top of a subducting slab. These are signals of ultra-high pressure metamorphism. To see such minerals at the surface, the rocks must have returned from depths where they spent only a short time in geologic terms. The path down and back is a riddle. One story holds that slices of the crust were carried down as part of the top of the slab, and then were buoyant enough to return along channels that opened as the wedge above them flowed. Another story holds that parts of the lower crust detached and rose as the surrounding rocks softened. The textures in these rocks are like hieroglyphs. Garnet crystals can trap tiny inclusions of minerals that reveal the pressure and temperature at the moment of growth. Some inclusions show that the rock passed through a stage where it held both coesite and more ordinary quartz as it rose. The grain boundaries can show how fluids moved, healing cracks and making new veins as pressure dropped. The ages of different minerals mark the timing of the plunge and the return. When we hold such a rock, we hold a message from a depth where continents rarely go. It came back slowly, slower than any elevator, yet fast enough that its high-pressure forms survived the ascent. All of these scenes belong to slow rooms within the same house, the quiet shelf that gathers sand, the rift that yawns and breathes, the basin behind a volcanic arc, the wedge of sediment at the trench, the long trough that leans against a range, the broad uplifts born of a hidden shallow slab, the hot breeze through a window in a plate, the subtle removal of carbon from the sky by water and stone, the green alteration of mantle rock that feeds life in darkness, and the bright crystals that tell of a deep visit and a safe return. Each part moves in its own time, yet all are linked to the deep convection that stirs the mantle and to the steady pull of gravity that asks mountains to share their heights with the sea. As you rest, imagine a shore in soft twilight. Waves arrive with no hurry and leave the scent of salt in the air. Beyond the horizon, currents glide over a burying slope where sand settles beside the skeletons of tiny drifting creatures. Inland, a valley deepens by a finger's width in a century as a rift opens. Far away, behind an arc of volcanoes, a small sea grows by the breadth of the mantle. At the great front where a plate descends, a wedge of mud takes one more slice and slides a little higher. In the lee of a rising belt, a plain waits to receive the next season of gravel and silt. Under the continent, a slab moves for a while as a flattened guest before plunging, and a pause in the voice of volcanoes allows cool mornings to settle on distant fields. Through a tear in the slab, warmth finds a path and writes a new line of vents across old hills. Clouds gather around a range where fresh rock meets rain and returns a little carbon to the sea. On a ridge in the ocean, deep water meets peridotite and makes a green mineral and a little hydrogen. In a valley of high mountains, a rock with a tiny diamond sleeps near a path where sheep walk in summer. Let your breath move as slowly as these scenes. The planet will keep writing while you sleep. Shelves will thicken, rifts will widen, wedges will grow, planes will deepen, slabs will change their angle, windows will open and close, rivers will wash fresh ions to the sea, serpentine will become a quilt in the deepest places, and bright crystals that once formed in the dark will wait in sunlight for gentle hands to find them. In the morning nothing will look different, and everything will be a little changed, carried forward by processes that do not rush and never tire. Deep in the roots of some mountain belts, there is a heavy secret that the peaks carry for a while and then quietly let go. When crust is thickened during collision, it pushes deep into the upper mantle and forms a bulb of cold, dense rock. Over time, that root can become denser still as minerals reorganize under pressure and as the base cools. If it grows heavy enough compared with the warmer material around it, the root can begin to sag. It stretches and narrows and then drops away like a slow tear sliding from a ledge. This is delamination. The falling piece sinks into the mantle, and warm, buoyant material flows upward to fill the space it leaves behind. At the surface, the mountains feel lighter. Valleys deepen as rivers respond to new gradients. Springs grow warmer in some places as heat finds new paths. Volcanism may return in a different flavor because the source region feeding melts has changed. In some ranges, you can read the story in a rise that comes long after collision should have ended. and in young lavas that carry crystals from deep sources that were once hidden by the heavy root. Delamination can happen in drips or in sheets. A small patch of dense rock can peel away and sink like a slow raindrop falling from a ceiling. Other times, a larger region detaches along a weak layer and slides downward as a broad slab. The signs are subtle. Seismic waves reveal where the lower crust has thinned and where a cool tongue of high-velocity rock has vanished. Gravity maps show where a buried load once pulled the surface downward. River terraces climb like old steps on the sides of valleys where uplift accelerated. Forests colonize new zones as snow lines lift a little higher. No one sees the root fall. The story is inferred from the whispers the surface makes as it adjusts, from the chemistry of young magmas, and from the quiet arithmetic of incision rates that rise and then relax as the landscape finds its new balance. Not every mountain core is a solid block that simply rises or falls. In some belts, the middle crust behaves like warm taffy sandwiched between a strong lid above and a strong base below. The heat that builds during thickening softens this mid-crust. Under the load of a plateau, the soft layer can begin to flow sideways toward places where the lid is thinner and the surface is lower. As it moves, it carries with it rocks that were heated and pressed into new forms deep below. These rocks rise along channels that act like hidden rivers within the crust. The surface above responds by stretching. Large, low angle faults can form that let the hot middle rise while the cooler lid slides away. Where these faults reach the surface, domes of shimmering metamorphic rock appear, ringed by broken blocks of the old lid that was peeled back. Geologists call such places metamorphic core complexes. They are windows into a level of the crust that usually stays out of sight. The textures in these risen cores are silky with aligned minerals that grew during flow. Micas glitter in planes that once slipped past each other, grain by grain. Garnet porphyroblasts sit like berries in a cake, holding tiny inclusions of quartz and feldspar that mark the path the rock took as it rose and cooled. Radiometric clocks in different minerals record different moments on that journey. One tells when the rock cooled through a temperature where a certain element could no longer move between crystals. Another tells when the last high-pressure mineral broke down into a lower-pressure form during ascent. Put together, the clocks reveal a rise that can be surprisingly quick in geologic time, measured in a few million years, guided by the interplay of erosion that removes weight at the surface and extension that opens a path from below. The landscape that wraps these domes often holds long, low ridges and wide basins, as if the crust sighed and stretched while the warm core came up to breathe. When a mountain system grows so broad that its interior is far from the edges where compression acts, it can rise into a plateau that seems to float near the sky. These are orogenic plateaus. They are made first by crustal thickening as blocks are stacked and burrowed one under another. Later, given enough heat, the lower parts can flow sideways like slow cream under a skin. The result is a great tableland with margins that are still being built, and an interior that is flat in the very large view, though it holds its own ranges and basins. On such a plateau, the air is thin and the sun is sharp. Lakes gather in closed basins because rivers that start in the interior often do not reach the sea. In the day, the shadows of clouds slide over distances that take hours to cross on foot. At night, the cold is close because the air holds little water. The wind has a long reach. Plateaus influence winds on a continental scale. A tall, hot deck in summer draws moist air inward from the surrounding seas and helps steer seasonal rains. In winter, the deck becomes a cold roof that pushes air outward. The margins of a plateau become bands where rains gather and release on one side, and dry shadows form on the other. The plateau also bears the marks of gravity that never rests. Where it grows too high, it spreads under its own weight and makes extensional basins along its edges. Where the deep root grows too dense, it may be removed by delamination, and the surface above rises in a broad swell. Volcanoes can dot the margins where mantle flow and crustal flow meet in complicated ways. The story is not one of a rigid table, but of a living tablecloth that shifts under the slow pressure of deep currents and the constant shaving of wind and water. Rivers that drain landscapes like these have their own agendas. A river cuts downward where fall increases, and it widens its valley where fall decreases. Headward erosion lets a river extend its reach upstream into the territory of another. When one river gains more energy, perhaps because of uplift in its lower course or because base level has fallen at the coast, it can gnaw its way through a divide and steal the headwaters of a neighbor. This is river capture. The result is a sudden change in the map of drainage that leaves behind curious features for those who move slowly enough to notice. There may be a dry valley that once carried a stream called a wind gap, now a gentle saddle crossed by deer and hikers. There may be a sharp elbow bend where a river left its old bed and found a shorter path. There may be a small stream that flows in the wrong direction given the tilt of the land because it is a remnant of the old network. Capture changes life along the banks. Fish that lived in one system find themselves connected to another. Sediment that once fed a delta now feeds a different reach. Terraces cut by the old flow hang above the new one like quiet viewing platforms. The reasons for capture are many. Tectonic tilt can give one river an advantage. Differences in rock type make one basin erode faster. A glacier can plug a valley and force a river to spill over a divide. Rebound after ice lifts one region and drops another. The proof that capture occurred lies in the geometry of valleys and the ages of surfaces, in cobbles that do not match their host basin, and in low divides where a small headwater has reached far into ground it did not own 1,000,000 years ago. It is the gentle theft of water written on landscapes that sleep and wake by millimeters. Where land meets sea, shore platforms cut by waves can be lifted in small increments to become terraces. The sea makes a broad flat at the foot of a cliff when waves attack it again and again. As sea level changes with the breathing of ice sheets, the active platform moves up or down. If the land is also rising because of tectonic uplift or rebound after ice, each still stand in sea level or each return to a similar level can leave another step in the staircase. Seen from the air, these terraces are graceful arcs that mirror the coast, each one a quiet memory of a time when waves paused there. Corals that grew on warm platforms can be dated with uranium series methods to anchor the story in time. Cosmogenic nuclides in surface rocks can reveal how long a terrace has sat in the sun. The spacing between steps records the pace of uplift against the rhythms of the sea. The terraces do more than mark motion. They stabilize slopes and give people places to live and plant. They hold soils that formed over long ages and that carry the imprint of ancient climates. They preserve shells and pebbles from beaches that no longer feel waves. Earthquakes can lift a coastal reach by the height of a person in a single event and leave an abrupt new step. Slow uplift can raise a terrace by the thickness of a fingernail each year. Put together across many cycles, a climb of several hundred meters becomes a quiet staircase that looks down on the present shore. To trace the line of old wave notches under an evening sky is to walk with the sea as it goes upstairs and downstairs through time. Faults that carry plates do not always release their motion with a sudden jolt. In some regions deep along the plate boundary, a slow slip event will occur. The two sides of the fault move by a few centimeters over weeks or months without sending strong shaking to the surface. This motion is often accompanied by a low, continuous tremor that sounds to instruments like rain on a distant roof. The event repeats at intervals that may be roughly regular. Scientists have observed such cycles along subduction zones and watched them to understand how strain accumulates and is released. The slow slip does not remove all stress from the shallower, locked portion of the fault. It may load that patch and affect the timing of the next earthquake there. The system breathes quietly in the deep, then occasionally coughs near the surface. On some continental strike slip faults, a different quiet motion occurs. Parts of the fault never lock fully, they creep. Over years, survey markers across such a fault show steady offset. Curbs and walls crack and move like slow chalk lines. The creep can be fastest on clay-rich or serpentinized sections that are weak even at low pressure. Where a creeping segment meets a locked one, stress can change. The locked part may be brought closer to failure by the gentle push next door. In the laboratory, rocks under controlled humidity and pressure sometimes slide in small leaps that repeat like a heartbeat. In the field, networks of instruments aim to catch these patterns to help understand how large ruptures begin. The lesson for our evening is simply that faults have many voices. Some are whispers in a constant murmur. Some are soft songs that return each season. Some are calls that come rarely and change a valley in a minute. Deep within sediments and fractured rocks, fluids move with their own slow agency. Organic matter buried in basins turns into oil and gas as it is heated and compressed. The liquids and gases migrate along layers and up faults, gathering in traps beneath seals of shale or evaporate. Over geologic time, they leak from those traps and are renewed as new layers are buried and cooked. Where migration reaches the sea floor without fiery heat, cold seeps form. Methane and other gases bubble out of sediments rich in shells of tiny creatures that were laid down in quiet water. Bacteria in the seep environment use methane and sulfur to make food. Larger animals host these microbes inside their tissues and farm them. The community glows pale in the light of a submersible white clams, tube worms, soft mats of bacteria covering the sediment like frost. The chemistry of fluids builds rock here too. Carbonate cements grow where methane is consumed, turning soft mud into crusts and chimneys. The seeps wink on and off as pressure and flow change in hidden layers below. On continental slopes, gas hydrates are common. These are ice-like crystals of water that cage molecules of methane. They are stable in cold conditions under pressure. Hydrates store more carbon than many forests. They line pores in sediments like delicate frost. When water warms or pressure drops, hydrates can dissolve and release gas that moves upward. Sometimes the rising gas makes pockmarks on the sea floor where sediment was expelled. Mud volcanoes can form where pressurized mixtures of water and sediment find a path. Over very long timescales, these deep fluids act as travelers who carry chemical stories from deep basins to the ocean and back into rocks. They can grease faults and help them slip slowly. They can also strengthen rocks by cementing pores. It is a quiet commerce between layers that never see the sun. In some basins, a very different material shapes the subsurface and even the surface over millions of years. Salt is strong grain by grain, but in layers many hundreds of meters thick, it can flow under pressure like a very slow liquid. As new sediment pours in and pushes down unevenly, the salt moves away from areas of greater load and rises where the load is light. It begins to form pillars and walls called diapirs. These climb through younger sediments and can reach near the surface. Their crowns may push up ridges and create a pattern of small basins and highs that control where rivers wander and where deltas choose to deposit. On images that show the subsurface, the salt looks like bright streams of toothpaste, smooth and coherent compared with the layered sediments it invades. Where a diapir nears the surface, groundwater reacts with the salt and forms a cap of gypsum and anhydrite and limestone that protects the mass below. This cap rock can host caves and springs. Over time, if the cap is breached, dissolution can make sinkholes that appear without warning in quiet fields. Offshore, salt forms long walls that channel the pathways of migrating oil and gas. Traps form where layers bend over the salt and where faults cut and seal against it. Engineers and geologists read these shapes to find resources, but under all of that, the simple physics is soothing. A material that is less dense and more mobile rises through a stack of heavier, stiffer layers as the pile above changes weight. The surface shows the ripples as gentle ridges and troughs on which forests grow and herons hunt. Beneath such dynamics lie blocks of crust that have changed little for billions of years. These are cratons. Their exposed parts are shields that hold old rocks like gneiss and granite, and greenstone belts that record volcanic arcs and oceanic crust from the Archean eon. The deep roots of cratons extend far into the mantle. They are made of mantle rock that has been depleted by ancient melting. That depletion makes the rock lighter and stronger than normal mantle. The result is a keel that stabilizes the crust above it. Diamonds ride to the surface in rare fast magmas that come from these depths. They bring tiny crystals of the deep mantle with them, gems and grains that tell of pressures far beyond those in ordinary rocks. Shields wear their age on the surface too. They hold belts of banded iron that formed long before oxygen flooded the oceans. They hold traces of old rivers that ran across plains where mountains no longer exist. They hold stable platforms where sedimentary rocks lie flat and quiet over the old basement. In these lands, very old faults can be traced for hundreds of kilometers, not because they move today, but because they mark contrasts in the very skeleton of the continent. The stability of cratons makes them the cores around which supercontinents gather. When plates rearrange, the cratons usually survive. They are the elders at the fire while younger lands come and go. Under all plates there is a boundary that separates the cooler, strong lid from the warmer, softer layer that convects. This is the boundary between lithosphere and asthenosphere. It is not a sharp wall, but a zone where temperature, water content, and grain size change how rocks deform. In oceanic regions, the thickness of the lithosphere grows with the square root of age as the plate cools while it moves away from the ridge where it was formed. Seismic waves that pass at different angles and frequencies can sense a zone of lower velocity that often lies just below the plate. Electrical measurements detect a layer that conducts more easily than the rocks above. Many lines of evidence suggest that in this zone, small amounts of melt or a bit more water or simply warmer temperatures make the rock softer. The plate can glide over this smooth layer as if on a film of warm wax. Beneath continents, the lithosphere is thicker in some places and thinner in others. Under cratons, it is very thick and cool, perhaps 2 or 3 times thicker than the oceanic lithosphere near ridges. Under rifts and young belts, it can be thinned and warmed, and magmas can rise along the thinned zones. In some places, the base of the lithosphere may drip downward, where it grows dense, much like the delamination of crustal roots above. The boundary breathes in geological time. When the base is warmed, the surface rises a little. When it cools, the surface settles. When water is removed by melting or added by fluids from below, the strength of the base changes. To imagine a plate is to imagine a raft with a slippery bottom moving over a deep, slow river. The raft can crack and bend and carry mountains, but its underside slides because the layer below is warm and forgiving. Let these scenes assemble now into one gentle panorama. A mountain sheds its heavy roots and rises by a whisper as the deep burden falls away. A warm middle layer flows and carries crystals upward to make a dome that shimmers in sun and rain. A broad plateau rests under a sky that feels close and guides winds across seasons. A river nibbles through a divide and steals a headwater, leaving a quiet gap crossed by deer. Old beach platforms climb a hill like a staircase that the sea once climbed and now has left behind. A fault beneath a forest moves without shaking for a month and then falls quiet. Bubbles of gas rise from a dark seep and feed a white garden where no sun reaches. A pillar of salt pushes aside clay and sand and makes a subtle ridge where oaks stand in a line. An old shield holds stones that remember a time when life knew no leaves, and under every scene a sliding base lets the plates drift with calm purpose. If you have stayed with me this far, let the last images be spare and restful. Night lies on a range where the stars feel close. In the dark, deep currents move stones no one will ever see. A root sags and a mountain lifts the thickness of a hair. Over a plateau, thin air carries a long wave of cold. A river runs quiet and then hisses as it falls over a ledge that it made long ago. Far at sea, waves trace long lines across a terrace that will be a step on a future hill. A fault sighs in slow slip deep underground. Methane beads rise like pearls from a small chimney and vanish. A salt dome breathes as more sediment arrives from a distant river. The old heart of a continent rests and holds its memories. The base of a plate slides forward by a distance shorter than your breath expands as you fall asleep. Thank you for sharing this quiet journey. The planet will keep its patient schedule while you rest. May your thoughts settle like silt in a calm bay, and your sleep be as steady as the drift of continents. Good night.